4.3 is broken into two portions. It's called Day 1 and Day 2 in your course notes, because that's how we also teach it in class. So it's the same type of setup for on campus. So we are on page 39 of your course notes. The top of the section on page 39 talks about a composite function. So this is hopefully something you learned also in algebra, although it might have been a while. And it talks about inputting one function in for the x value in another function. Okay, so as it is noted here, g of x then would get plugged in for the x term in the function f. So in example 1, it asks us, it gives us f of x equals 3x squared minus 1 and g of x equals x plus 5. And for part A, it asks us to find f of g of 2. Okay, so there's kind of two things going on here. We are finding the inner part, g of 2, and then we're putting that in that function into the outer function, f. So you could do it a couple different ways. You could find f of g of x first, or you can find g of 2, and then whatever that value is, plug it in to the function f. I think that is probably easier in this case. So again, first, we're going to find g of 2. So we're plugging 2 in for x in g of x. So we would get 2 plus 5. We're looking right here. Plugging in 2 for x, and we get 7. So then the second step is now we're applying our outer function. So we are plugging in g of 2 into the function f. So f of g of 2 is the same thing as f of 7, because we are plugging in this in for the g of 2. So f evaluated when x is equal to 7 would be 3 times 7 squared minus 1. So 3 times 49 minus 1. And we would get 146. You can use your calculator to approximate that. Okay. Part B is similar. We're asked to find g of f of 2. So we would first find f of 2 and then plug that into the function g. So I'm going to do it off to the side. So to find f of 2, we plug 2 in for the x in function f. So we have 3 times 2 squared minus 1. So 3 times 2 squared, well, 2 squared is 4. So 3 times 4 is 12. 12 minus 1 is equal to 11. So instead of g of f of 2, f of 2 we just found was 11. So this is the same thing as g of 11, plugging 11 in for x in the function g. So we would get 11 plus 5, so g of 11 is equal to 16. Now, part C and D are not asking us to evaluate them at a specific point. They are just generically asking. Part C says f of g of x. So we're leaving the x in. We're not plugging in any numbers. And we're evaluating this new composite function. So again, the inner function is getting plugged in to the outer function. So in the function f, instead of just f of x, we are plugging all of g of x. So for this one, we're plugging all of g of x in where the x is in the function f. So instead of 3 times x squared, instead of x, we're plugging in x plus 5. Okay, now this is good, but then we should also probably simplify it. So remember when we have x plus 5 squared, I'm going to do this in another color just for clarity. Instead, when we have x plus 5 squared, that's the same thing as x plus 5 times x plus 5. So we have to actually FOIL it, this portion, and then keep our minus 1. So x plus 5 times x plus 5 is x squared plus 10x plus 25 if you FOIL it, distribute our 3, we get 3x squared plus 30x plus 75, and don't forget to include your -1 at the end. So our final answer would be 3x squared plus 30x plus 74. So that is what f of g of x is equal to. Now, for part D, they're asking for the inverse. So they're asking for g of f of x. So now we are plugging in the function g. I'm going to do this in a different color. Actually, I'll just erase this real quick so it's clearer. So we're plugging in our function f in for the x in g. Okay? So again, the inside function gets plugged in to the outside function. So instead of the x plus 5, we plug in the entire function f of x. I put parentheses just to keep it clear, but they're not really necessary. So we have 3x squared, and -1 plus 5 is a positive 4. Okay, the next page of your course notes already has example 2. Very similar, but we're kind of looking for the inverse. So we're kind of going backwards from what we're given. It says if f of g of x is equal to the square root of x squared plus 1, what are f of x and g of x? So notice here that g of x is inside the function f. F is the outer function. So g of x in this case would be equal to x squared plus 1 because that's what's inside here. And then the outer function would be square root of x. Okay, so when we find the composite f of g of x, which is x squared plus 1, would be plugged inside the radical, right? All of this will get plugged in the radical. So it's kind of a check to see that we are correct. Okay, so now what is the derivative of f of g of x? So again, this is calculus, right? So we know we're going to want to talk about derivatives and limits. So we already know that the derivative of f of x is the limit as h, this is most commonly what we're going to use, the limit as h approaches 0 of f of x plus h minus f of x over h. So we established that before. Okay, now let's use the alternative form though. The box blue one is what we typically use. Let's use the alternative form to find the derivative, to find the composite function, f of g of x. So if y equals f of g of x, then the derivative, notice that we're just plugging g of x into the function. So instead of f of b, we would say f of g of b minus f of g of x. So instead of f of x, we're plugging in the g of x over b minus x. Okay, so here when it says f of b, again, we're plugging in g of x. So that would be f of g of b, because our b is our x and we're taking the composite. This gets a little confusing. Don't spend too much time staring at this, but we will be using it. We won't be using the whole process. We'll be using our end result. Okay, so looking at this point, they're simplifying it a little bit. They're simplifying it a little bit by multiplying by 1. By multiplying, this term is the exact same in the numerator and denominator. So we're basically multiplying top and bottom by 1, right? G of b minus g of x divided by g of b minus g of x. Okay, now it doesn't seem immediately obvious, but if you look at the next step, they just switched the denominators, right? So they switched them, and the reason for that, and now we're going to apply the limit to both of these, okay? And the reason for that is then we can see that this is the definition of the limit of f prime of g of x in the second portion is equal to the definition of the limit of g of x. Okay, now notice that this allows us to think of it differently. So instead of the derivative of the whole thing, we are taking the derivative of the first function, plugging in g of x, and then multiplying by the derivative of the inner function. So most importantly, don't try to take too many notes. Don't worry about this too much, but let's look at what this looks like to our definition. We have, let me look for the beginning. So we have, if y equals f of g of x, then the derivative of y is equal to this last portion, f prime of g of x times g prime of x. So we're going to use this, but we're going to rewrite our function a little bit. Now, this is not necessary. If the last way I just did it makes sense to you, that's fine. But here's another way of looking at it, applying the rule from this slide. Action. Okay. So it says, example 3, find the derivative of y if y equals 2x cubed plus 9x plus 5. So what this means is we can take the derivative. This is like a composite function, right? 2x cubed plus 9x is on the outside, is on the inside, excuse me, and the fifth power is the outer function. So the way this works, and this is going to be called the chain rule from now on. Whenever I mention chain rule, this is what I am talking about. Okay, we're going to take the derivative of the outer function and then multiply by the derivative of the inside function. So here, the outer function is the fifth power. Okay, so we're going to take a 5 on the outside. Okay, so the exponent gets multiplied in front as if this inside term was one variable, and then we reduce our exponent by 1. And then what we just found in the last slide was that then we would multiply by the derivative of the inside function. So now we're going to find the derivative of what's under, or the inner function. Okay, the derivative of that. The derivative of 2x squared would be 6x squared. The derivative of 9x would be 9. Okay, now we are not going to multiply this out. This is our final answer. The point is to find the derivative, not to do a whole bunch of algebra. We do not want to take the binomial to the fourth power. That would just be a lot of extra work. Okay, now we will see this over and over. It will be confusing at first, but we are going to do this repetitively throughout the whole semester. Use it. So just remember, it's called the chain rule. So again, we're taking the derivative of what we would consider the outer function. So the big exponent in this case are same rules we used before. Multiply the exponent in front, decrease the exponent by 1, but then we multiply the whole thing by the derivative of what's on the inside. Okay, so let's go back. So we're going to slide previously. Okay, so opinion, if you can picture the outer function and the inner function, and then apply the chain rule, so take the derivative of the outside, the bigger portion, which would be the fifth exponent, and then multiply by what's the derivative of the inside. It's a little bit easier to manage. Okay, example 3 is another way of looking at the example we just did. If we rename our terms a little bit, okay, we're going to say let our inner function, g of x, be equal to x cubed plus 9x. Okay, and then we're going to let f of u, instead of y, we're going to have a u. And this is also called u substitution. Okay, so we're going to say u is equal to g of x. G of x referring to our rule we had on the last slide. Okay, so then f of u, instead of y equals or f of x equals, we'll say f of u is equal to u to the fifth, right? All of this is u. Now, looking at our rule from the other side, it's also written here. y prime would be equal to f prime of u, so the derivative of f of u times the derivative of g of x. So if we find the derivative of f of u, we just multiply our exponent in front, reduce the degree of our exponent by 1. So subtract 5 from 5. 5 minus 1 is equal to 4. Now the derivative of g of x would be equal to 6x squared plus 9. Okay, so now applying this, now going back, so the actual equation is equal to 2x cubed plus 9x all to the 5th. So a rule says that would be equal to f prime of u, 5u to the 4th, times g prime of x, right? So we're just plugging in these values. Now, we really don't want a u in our equation, right? Because our original equation doesn't have u, it just has x. So now we're substituting back. So u is equal to 2x cubed plus 9x. So substituting back, we have 5 times 2x cubed plus 9x to the 4th times 6x squared plus 9. Now notice this is the exact same solution we have. If you want to use u substitution, you would say the inner function is equal to u, take the derivative of that, and then take the derivative of what's inside and substitute back. Whichever makes more sense to you. In my opinion. Okay, so some more examples. And this is page 41 of your course notes. Okay. So again, we want to look at what's the outer function and what's the inner function. So remember that the square root is equal, let me fix that. Square root is equal to the 1/2 exponent. So the 1/2 exponent applied to the entire thing would be like our outer function. So we could color coordinate this so you could visualize it even more. This 1/2 exponent is the outside function, and this 1 minus x squared is the inside function. Okay, so we first take the derivative of the outer function. So the 1/2 comes in front. We decrease the exponent by 1. And what's inside the function stays the same. And then we multiply by the derivative of the inner function. Okay, so we're multiplying by the derivative of 1 minus x squared. So the derivative of 1 is just 0. The derivative of negative x squared would be negative 2x. Now, this can easily be simplified a little bit, right? We would multiply the 1/2 and the negative 2x together in front. So 1/2 times negative 2 is negative 1. We still have the x, and then 1 minus x squared to the negative 1/2. And there's no need to convert this back to radical form. Just leave it as an exponent. Okay. Part B. Now again, the 4th exponent is our outer function. So if we rewrite this, the outer function is in blue. We could rewrite the inside function in red. Okay, so when we find the derivative, we take the exponent, multiply it out front, decrease the exponent by 1, and then we have 2x minus 5 still on the inside of this function. And then we would multiply by the derivative of what's on the inside. So the derivative of 2x minus 5 is simply 2. Okay, so we can just multiply these consonants, right? Not consonants, constants. 4 times 2 is 8. So we have 8 times 2x minus 5 to the 3rd power. Again, that's the derivative. So that is the answer. All right, another example. So if I were you, I would pause the video at this point or at any point, and go and do some examples in the homework, and then come back. That way you know if this is making sense or not making sense. It can really help you in the learning process to do some hands-on in between watching someone else do it. So again, for this example, we're going to rewrite the radical as an exponent. So instead of the square root, we're going to write that as the 1/2 exponent. Okay, so let's keep one color this time to see if we can keep this straight in our head. So we're going to take that 1/2, multiply it in front. The inner function is going to stay the same, and then reduce the exponent by 1. 1/2 minus 1 is -1/2. And then we multiply by the derivative of what's inside the parentheses, of the inner function. So derivative of 1 minus 7x is -7. Okay, now we can multiply these constants out front to combine them and simplify this a little bit. So 1/2 times -7 would be -7/2. Next example. Okay, in this case, the 3 multiplying out front, we can just kind of ignore, right? So we're going to keep that there, but the outer function is still that -5 exponent. Okay, now we do not need to write this as a fraction. Just leave the negative exponent alone. Our derivative rules still apply as usual. So when we take the derivative, we multiply the exponent out front. So we would have 3 times -5 would be -15. And now when we reduce the exponent, -5 minus 1 would be a -6. So instead of, it's very tempting to put -4, right? But that would actually be adding 1. We subtract 1 from our exponent. And then we multiply by the derivative of the inside function. So the derivative of x squared is simply 2x. So multiplying those out front, to simplify it, we would have -30x times x squared plus 1 to the -6th. All right. Yet another example. Getting close here, guys. For this one, the cube root, remember, is the same thing as the 1/3 exponent. So instead of the cube root to find the derivative, we're going to write that as to the power of 1/3, and we continue the same way we have before. So to find the derivative, we multiply by the exponent out front. Don't forget that negative, just leave it there. 2x to the 4th plus x. Subtract 1 from the exponent. So 1/3 minus 1 is a -2/3. And then apply our chain rule. We multiply by the derivative of what's inside the outer function. So when we find the derivative of this, derivative of 2x to the 4th would be 8x cubed. Multiply the 4 out front, decrease the exponent by 1. And the derivative of just x is 1. Now, we are not going to multiply this out, right? So we would just leave it as it's written because it's a binomial. In the last couple, it was just one term, so we could just easily multiply it out front. But that's not the case here, so we will just leave it alone. So we have y equals 2x cubed plus 9x to the 5th power. Okay, so again, our outer function, the 5th power, gets multiplied in front. We decrease the exponent by 1, so 5 minus 1 is 4, and then we multiply by the derivative of what's inside the function. So the derivative of 2x cubed would be 6x squared. The derivative of 9x is simply 9. And this is F. For part G on page 42, we are going to rewrite a little bit. So this one's actually different in the sense of how it's written. Notice there's an exponent of 2 and a radical of 5. So if you review your algebra a little bit, if you need to, we will say that this is the exact same thing as, oh, I missed my plus 1. The exact same thing as the 2/5 1/5 exponent, right? Because it's the entire term is squared, and then it's to the 1/5. If we want to add a step in between this to help clarify that, oh, that's not what I wanted to do. I wanted to write an exponent of 3x plus 1 squared, and then instead of the fifth radical, we would say that's the same as the 1/5 exponent. And our exponent rules say if we have one exponent raised to another exponent, we would multiply these, right? 2 times 1/5, which is what I have, 2/5. And once it's written in this fashion, it's much easier to see how we would apply our chain rule. We multiply our exponent in front of the outer function, decrease the exponent by 1, so 2/5 minus 1 is a negative 3/5, and then multiply by the derivative of what's inside. The derivative of 3x plus 1 is 3. Now, to simplify it, we can multiply the 2/5 and the 3. So we would get 6/5 times 3x plus 1 to the negative 3/5. Again, there's no need to put it back in radical form. Just leave it like this. Okay. One more example, part H. We again proceed just as before. So the outer function is that negative 3 exponent. So we're going to multiply it out front, get negative 6, and then decrease our exponent by 1. So negative 3 minus 1 is 4. And then we multiply by the derivative of the inner function, what's inside the parentheses. So that would be 12x plus